Then to all, I'm Samender, Assistant Professor in CSC Department. My college name is AKGEC Engineering College. So in today's session, I will cover a gradient method, that is Nesterov'S accelerated gradient method. My today's course outlines its advantages and disadvantages of gradient descent. As in the last session, I will cover gradient descent. So in this particular session, we are starting with to discuss about what are the advantages and disadvantages of gradient descent. The gradient descent is already discussed, so we will talk advantage and disadvantage. After that, we will cover types of gradient descent. It is also a very important topic as far as our exam concerned. Then we will cover two basic optimization techniques. First is Frank-Wolfe method and second is Nesterov'S accelerated gradient method. If time remains, then we will cover operator splitting method and Lagrangian multiplier. And in the last, we will solve some numerical by means of Lagrangian multiplier. So, as a starting, we will start the advantages of gradient descent. So, what are the main advantages of gradient descent? As it is very, very useful, or we can say it is widely used. Gradient descent and its variant are widely used in machine learning and optimization problems because they are effective, easy to implement. So these are two qualities through which it made first choice for their use. As we can say, today are the era of machine learning, and in machine learning we generally take problems related to optimization, where we need such algorithms which are very, very effective. So gradient descent is very effective as far as its effectiveness is concerned. So easy to implement and very effective. This is first advantage of gradient descent. Then second is what? Convergence. Gradient descent and its variants can be converged to a global minimum or a good local minimum of the cost function. We already covered what is cost function. So local minimum of the cost as optimization problem, we have first condition. The cost function will be minimum depending on the problem and its variant use. So this is second advantage. And then third is scalability. Many variants of gradient descents can be parallelized and scalable to large data set and high dimensions model. So it is very useful for high or large data set. And last, flexibility. It is very, very important topic. Different variant of gradient descents offer a range of trade-off between accuracy and speed and can be adjusted to optimize the performance of a specific problem. So related to our problem, it is very, very flexible. Now these are some disadvantages. What is choice of learning rate? We already discussed what is learning rate. So learning rate is a very, very big disadvantage of gradient descent. The choice of learning rate is crucial for the convergence of gradient descent and its variant. Choosing a learning rate that is too large can be lead to oscillations or overshooting, while choosing a learning rate that is too small can lead to slow convergence or getting stuck in local minima. So we need a very specific or very appropriate learning rate. So as we already covered, let's take a simple function fx, and we need to find minima of this particular function. If we talk about learning rate, if it is very high, suppose it is high. So after each iteration, suppose we are starting with this point, the next point will be this one for high learning rate. And in this way, this is next iteration, then next iteration, then next iteration. So you can see in this movement is zigzag. So our minimum point will be loose, or we can say we can't find the minimum point of the function. In the same way, if we talk about the low or very minimum learning rate, so this process will become very slow, starting with this, then this, then this, then this, then this. At every iteration it will find a local minima, which is also not a good thing. So this is our first disadvantage of gradient descent. That is what is choosing a appropriate learning rate. It can't be maximum, or we can say high, or it can't be low. So this is first disadvantage. Then sensitivity to initialization. Gradient descent and its variant can be sensitive to the initialization of the model's parameters, which can affect the convergence and the quality of solution. So this is also a disadvantage. Means choosing initial point is very difficult, or we can say sensitive. Next is time consuming. It is very name method. So as an initial optimization technique, it will take more time, or we can say time consuming is a very big concern. So gradient descent and its variant can be time consuming, especially when dealing with large data set and high dimensional model. The convergence speed can also vary depending on the variant used and the specific problem. At the time when this algorithm is evolved, at that time we don't have very big data sets, so at that time it is perfect. But nowadays we have very big, very large data set on which we are going to implement this large data set. This is not efficient, or we can say it is very time consuming. So this is also a very disadvantage of gradient descent. Next is local optima. So the gradient descent and its variant can converge to a local minimum instead of the global minima of the cost function, especially in non-convex problem. This can affect the quality of solution, and techniques like random initialization and multiple restarts may be used to mitigate this issue. So as this diagram shows, we can easily find this may be the minimum point. But when we implement, or when we can say we want to find the minimum point, so this is not good algorithm. Since we are start with any random point, suppose we are starting with this one, so at every iteration it will give a new point, or we can say new minima, which will be the local minima, not the global minima. So this is also a disadvantage of gradient descent. So our next topic is gradient descent, or types of gradient descent. So there are basically three types of gradient descent. First is normal, or we can say batch gradient descent. It is very simple or general gradient descent. Next is updation on it, stochastic gradient descent. This is second type. It is updation on first one. And last is mini batch gradient descent. It will contain property of both the upper types of gradient descent. So starting with batch gradient descent, it is used to find the error for each point in the training set and update the model after evaluating all training examples. This procedure is known as the training approach. In simple word, it is the greedy approach where we have to sum over all examples for each update. So it is a very naive technique to find the error in the given data set. So in the complete data set and find the error in entire data set. This is so advantage of batch gradient descent will be it produces less noise in comparison to other gradient descent. So it having less noise. It produces stable gradient descent convergence. Stable. Second advantage, and it is computationally efficient as all resources are used for all training samples. So this is the third advantage of this batch gradient descent. So these is thing. So our second type is it is far better than the previous one, or we can say it is updation of batch gradient descent. So second is stochastic gradient descent. So it is a type of gradient descent that runs on one training example. It is running on one training example per iteration. So it will clearly suggesting that each iteration it will run on one training set. Or in other words, it processes a training approach for each example within a data set and updates each training example's parameter one at a time. Now, these are the advantages of stochastic gradient descent. So first is learning happens on every example and it consists of a few advantages over other gradient descent. So every model, or we can say every data set will be treated like a new example. It is easier to allocate in desired memory. This is the main advantage of stochastic gradient descent. Next is it is relatively fast to compute than the batch gradient descent. So we can say as comparing to batch gradient, it is much faster. And last is it is more efficient for large data set. As I already told you, gradient descent is not efficient for large data set. If we talk all the three types, so this will be the more efficient for large data set. So this is primary. We can say this is the advantage of stochastic gradient descent. And last is mini batch gradient descent. This will contain property of both previous gradient descent. So mini batch gradient descent is the combination of both batch gradient descent and stochastic gradient descent. It divides the training data set into smaller batch sizes and then perform the updates on those batches separately. So big data set can be split into small data set. Small. So on processing, small data set will be more efficient as compared to large, or we can say big data set. This is how it will efficient its processing. And advantages of mini batch gradient descent is it is easier to fit in allocated memory. As it is divided the data set into mini data sets, so it is easier to fit these mini data set into allocated memories, and it is computationally efficient. Efficient will be since data set is very small. This is D2, second data set. And last is it produces a stable gradient descent convergence. So these three are the types of gradient descent. I will cover advantage of each type. Next is very famous optimization technique, that is Frank-Wolfe algorithm. So it is an iterative first order optimization algorithm for constant convex optimization. Again, we have number of constant and we are going to optimize the given function. It is also known as conditional gradient method, reduced gradient algorithm, and the convex combination algorithm. All the three names suggest that it is a updation, or we can say enhancement in the gradient descent. So as an initial points we have same function and constant. So we will cover. The method was originally proposed by two scientists. First is Marguerite Frank and second is Philip Worth in 1956. On both scientists' name, it will give the algorithm name, that is Frank and Wolfe. In each iteration, the Frank-Wolfe algorithm considered a linear approximation of the objective function and moves towards a minimizer of the linear function take over the same domain. It's particularly useful when the feasible set is a convex set and the objective function is differentiable. So here we have two primary conditions. First is the set, a feasible set must be a convex set, and second, the objective function must be differentiable. So these are the two primary conditions. Now, what is our objective? To minimize a convex differential function. Let the function is fx over a convex set C. This is our domain. Now these are the steps to solve any numerical. So first is initialize. So start with an initial feasible solution x0 inside the convex set C. So this is our first step. Choose a step size rule using a line search or fixed step size. This is our first step, that is initialization, and then take the size rule. And second is iteration. So each iteration t compute the gradient. So we need to gradient fx. So gradient is what? We will take differentiation of the function with respect to given variables. In this particular case, we have one variable x, so we need to differentiate it this function fx. That is gradient. Find a direction dt that minimizes the linear approximation of this x. Step is t plus d. Subject to the convex set C. So this is our convex set C. Then update the solution. So this is basic formula by which we are processed to optimize the given function. The formula is x t plus 1 step will be xt plus alpha t dt. What is alpha t? Alpha t is the size rule as discussed in the first step, where alpha t is the step size. So we are iterating this. So the last is when to stop. The stopping criteria will be repeat the iteration until a convergence criteria is met. That is small gradient norm or a small improvement in the objective function. So this is an example we need to solve by means of Frank-Wolfe method. We have given objective function, that is fx is equal to 1 by 2 x square subject to the constant. Constant is given. We have values that will come under 0 or 1. This is our convex set. So these are two things. first objective function that we are going to optimize, and then we have given convex set. So objective function feasible set. Let's start with step number 1. We need to initialize it. So our initial point will be x naught, that is 0.5. Choose a step size rule. Let's say alpha t will be the 2t plus 2 for each iteration. This is our step size. So iteration at each iteration t, compute this one. So first we need to differentiate it. If we are differentiate this one, so what will be 2x? So we can say x is our gradient descent. Fx will be equal to x. Find the direction dt by solving algorithm on this one. This is domain that will remain under C, or we can say convex set. So this is gradient of x fd, and this is d, which simplify dt to minimum value. So this is how we can find the minimum of the given function. Next is Nesterov'S accelerated gradient descent. It is also our new topic. So we will cover this topic in next section.